What we're going to do today is walk together an actual example where we'll be running the pipeline to process some simulated MIRI integral field unit data through the pipeline. So if you look in the list of files we've got in the file browser here on the Jupyter Lab, you're going to look in this MIRI MRS folder here, and you'll see two notebooks in there, Notebook 1 and Notebook 2. For today, we'll be walking through Notebook 1, and what this does is it steps through the individual pieces of the Spec 2 and Spec 3 pipelines, showing you what the input and the output is of each one, talking about a few caveats, how the step works, etc. That's useful for learning how the pipeline itself works. It's going to work with just a single one of the MRS grating settings for illustrative purposes. It's not how you'll actually be processing the data that you get off the telescope in real time, in the sense that the pipelines are designed to just flow information from one step cleanly into the next step. So Notebook 1 isn't designed to go efficiently through multiple gratings, to combine those gratings, to process large quantities of data, etc. So if you're interested in looking at how you'd process data you really get in flight, you're welcome to also look at Notebook 2 on your own time. That'll be the subject of JWebbinar number 5 coming up in a couple of weeks or so. But for now, at least, let's open MRS Notebook 1. And I can page down just a little bit to show you how it is that we'll be working through this. First, I'll tell you a little bit about the data that we're actually going to be simulating coming from MIRISIM, the MIRI instrument simulator. I'll show you how we're setting up the pipeline to pull in the latest reference files and defining the actual pipeline function statements, where your data lives, etc. And then walk through the individual pipeline steps, showing you what the inputs and outputs of each look like. So this is really designed as a reference guide that you can use both now on and later. In the sense you can use the simulated data that we're providing to run through this notebook. You can put your own simulations into it. You could even put real data, once that exists, into this notebook as well. It's designed as something that you can read through and then tinker with pieces as necessary as you want to understand how different parts of the pipeline work. So I'll skim down and say we're going to start with this kind of an object here. We're going to be talking about a simulated object that is just a single point source in a field of view with some astrophysically realistic spectrum, in this case taken from the active galaxy NGC 5728. We're going to simulate that just through a single band of MRS data, so a small little piece of this wavelength range, just for illustrative purposes. Again, if you're interested in issues involving the whole wavelength range, then come back again in 2 weeks, and we'll be talking about that in a bit more detail in Notebook 2. There's a bunch of caveats I put in here about simulated data that I won't list all of them off in real time. It's provided as mostly a reference point for if you're interested in using your own simulations to explore the pipeline properties. Here's a bunch of gotchas to keep in mind. There's a lot of limitations in the simulated data, things that don't interact perfectly with the pipeline, things that aren't quite in place, and just things to be aware of, either in how you modify the pipeline or things to keep in the back of your mind when you're looking at the results you're getting out the other end of the pipeline. I'll move down to the setup next, and again, I'll skip all the words because the words are essentially what I'll be saying over the course of the next half hour. And we'll start with this first cell here. You can follow along with me from this point. This is going to be the first cell that you can shift enter on as we go through the rest of the notebook in order to keep up with what I'm doing. What this cell is doing, it's setting something called the CRDS context. It essentially means what version of the reference files are you pulling in with the pipeline. Ordinarily, this is something you won't need to worry about too much when running the pipeline. You'll run whatever the latest and greatest version of the pipeline is. It will pull in whatever the latest and greatest version of the reference files is. For a variety of reasons, we're actually working with a slightly outdated pipeline today. We're working on the 1.1.0 pipeline, or what was the latest as of February. There's been some change in reference files since then, and this override essentially just says pull in this particular context that I know happens to be a more recent version. This is, again, something you won't need to worry about later. Another point I should caveat, though, for the notebook today, I'll be talking about what was in the pipeline as of February. I won't be talking about the new things that are under development, things that have happened since February, things that will happen over the course of the next couple of months. I'll touch on those occasionally, but I won't be focusing on them, obviously, since there's not as much to show. We can keep shift entering down, and we come now to the actual Python section of the notebook, where we're starting to import things of interest. Loosely, it breaks down into basic system shell utilities, utilities for working with the data. These are the lines of interest for actually dealing with the JWST pipeline. These are where we're importing the entire Detector One, Spec 2, Spec 3 pipelines as a block. And here's where we're importing the individual steps. Ordinarily, you wouldn't need the individual steps because the pipelines just naturally run from one into another, but because we're breaking it out today, that's why you're seeing those split out here. And then a few additional utilities for working with the data that I'm pulling in as well. So as far as setting up the data I/O, we're actually going to be cheating a little bit today. We were not going to run the entire full pipeline through. And the reason why is because there's some steps of the IFU pipeline, cube building in particular, that take quite a long time to run. So if we ran all of the steps in this notebook through from beginning to end right now, it would take about an hour and a half, and nobody wants to wait around just waiting for pipeline steps to run today. So what we're going to do is we're going to use a cached directory of pre-reduced data. And in cases where the pipeline step can run quickly, we'll run that in real time today. You'll be able to see the outputs of the logs. And in cases where it takes a little bit longer to run, then that's going to instead pull data out of this cache. You can go back later and redo all of these long steps if you like as well. There's this reprocessing flag I've set, redo long. I've got it set to false. We don't want to redo long pipeline steps for purposes of this demo, at least. But later on, if you want to redo them, you're welcome to just set that to true, run the notebook, and you'll actually see them all chunking out one after the other as it redoes all those steps. Again, we'll keep it for false for right now, though. A little bit of an explanation of how I've got the data directories set up. I've tried to have this mimic what we'd actually be getting when we're working with flight data. We've pulled data down from MAST. We've got the raw data sitting in some directory on our computers. This stage 0 directory is where I've got it. In this case, it's the MIRI sim, the simulated data inputs. And I like organization in my data product, so I've actually got all the different stages going out into different subfolders. Stage 1 detector products, stage 2, stage 3, etc. There's a little bit of extra code up here just to tell it where to pull data from in the cache if we're running in this special method where we skip long steps. But that's just a detail on the back end that you won't need to worry about. So with that preamble out of the way, let's go on down to the Detector One pipeline. So this is something that's been explained in rather more detail in previous JWebinars, and I won't be going into a lot of detail about what the individual steps in Detector One are doing. In brief, again, it's just going from the uncalibrated slope images to the uncalibrated ramps, where you've got the individual readouts from the detector, and it's taking that to the uncalibrated slope images, where now you've just got a dn per second value at each pixel. We do have the running of that in the notebook, though. Here's how we're doing it. First, we're going to define a function that will call the Detector One pipeline. So I'm just saying now, here is an instance of the Detector One pipeline I'm going to be calling. I'm going to make a couple tweaks to how I want that pipeline to run. I'm going to send it out to a special directory. I'm going to do a special parameter override. I'm going to tell it to skip the reference pixel subtraction step. The reason I'm doing this is one of the entries above in my gotchas about MIRI simulated data, in the sense that the simulated doesn't process reference pixels in the way that the pipeline is expecting from flight data. And that means you can get weird artifacts coming in if you run the flight pipeline calibration on the simulated data. And the best way around this is just to skip reference pixel subtraction when working with MIRI simulated data. So that's what this is doing here. So this defines the function that we want to run on the data. This just looks for the input exposures in our input folder. You can see it says it found 4 to process. It's just a single 4-point dither for a single band. And then this cell here would ordinarily run the pipeline on those steps. It would say, now for each file in my list of simulation files, run the Detector One instance on that file. However, now this step takes 10, 15 minutes or something to run on all of these different exposures. So what we're actually doing, because we've got this redo long flag set to false, is just copying those out of cache to our output directory. So you can look at them in the expected place, but we didn't actually run the pipeline just yet. We can take a look at them quickly, just to have an idea what it is we're working with. So we can search for these so-called rate files. It finds, again, all 4 of them that we're expecting. We can open it up to take a look at the contents. You can see it's a multi-extension FITS file. It's got a science extension, which is where most of the objects of interest actually live. This is the flux from your source. It's got a corresponding error plane. It's got a data quality plane telling you about what's going on in any individual pixels, if there's some that are bad that you should ignore, etc. And it's got a few other things as well that I won't be going into now. We can actually take a look at them visually and see what they look like too. So what I'm plotting now is the uncalibrated slope image of the two of the 4 MOS exposures. This is a point source. You'd be excused for not having that be obvious when you look at it, in the sense that it doesn't look terribly point-like. But the reason why is because MOS is a slicer IFU spectrograph. It's got multiple different slices dispersing the light from each part of the focal plane. And this is channel 1 on this half of the detector, this is channel 2 on this half of the detector, and each of these slices just samples a different part of your point spread function, and it's dispersing up and down in this direction. You can tell that it's dithered between the two exposures because these bright columns move from this part of the detector over to this part of the detector over here. But it takes a while of looking at the data before you get to look at these exposures of raw data and just say, oh yeah, that's a point source and it's dithered. And later on, we'll actually look at it in a slightly more intuitive framework. So we can keep going on, and now we're going to look at where the pipeline gets more interesting, at least from today's purposes, the Spec2 pipeline. The first step there is the assign WCS step. And what I'm going to do on the next few steps, I'm just going to shift enter through all the steps associated with that part of the pipeline so that it can run while I talk about it. So it's going to run, I'll scroll back up and then talk about what it's doing. So here we had the same kind of approach we had for the Detector One pipeline. We defined an instance of the assign WCS step. We're using the call approach in this example, and we're just calling on each one of those individual input files. And you can see it printing the outputs about what it's doing as it runs through the pipeline. It's saving the model, etc., looping on to the next one. This is a step that really you'll never want to skip when you're running the pipeline, because this is what tells the rest of the pipeline where your data is in the sky. This is how you map individual detector pixels to something of astrophysical interest in terms of sky coordinates. So we can look at what it's attaching onto that by looking for the output step files that it's produced. These are rather long and unwieldy file names, but again, you'd usually never be working with these intermediate files. They just get passed naturally into the next stage in the pipeline. If we open that file using the JWST data models, it'll give you an example about the coordinate transforms that are available to you. What it's done is it's used the instrument distortion model and put that together with information about the telescope pointing into a set of functions, essentially, that are attached to your FITS data products now that allow you to do these distortion transforms from, for instance, the detector reference frame, a few different internal reference frames, and finally out to the world coordinate reference frame. If that's something that you want to dig into to really learn what's going on in individual parts of your detector, you can query it directly. If, say, you really wanted to know what's pixel x equals 376, y equals 589, what does that mean in a physical sense? You can call those transforms and it'll spit out at you, this is this array, this deck, and this wavelength for this individual pixel. So that's something that you can look into later if it's something that you're interested in testing about your data. The next step of the pipeline is the pixel-wise background subtraction. And again, I'll shift enter through the actual cells in that pipeline so it can run while I talk about it. This is the first of 3 places in the pipeline where we can do background subtraction. So what's happening in this kind of it, the Spec2 basic background subtraction, this is a pixel-by-pixel background subtraction method. So this is kind of a placeholder in case it's necessary and we can't do anything smarter, if you will, with how we're doing our background subtraction. A fallback option is going to be you can just take an image 1 minus image 2 and just do a difference to subtract off what your background term is. So if you're looking at a point source, for instance, you could subtract off the 2 nods from one another. If you're looking at an extended source, you could subtract a dedicated background pointing that you might have attached to your observation. And this should do a good job of subtracting off an arbitrarily complex background due to, say, the telescope thermal component. It's not really ideal from a noise perspective, in the sense that because you're doing pixel by pixel subtraction, any noise in your background will also show up as noise in your final data products. And we're hopeful that we won't actually have to do that. So there's a couple steps later in the pipeline where we do something slightly smarter about the background subtraction, but this is in here in case we actually end up needing it based on flight and commissioning data. So this is just, if you wanted to call this pipeline module at the moment, here's how you'd set it up, defining background files associated with individual pointings. And if this is something we need to do in flight, there will be an automatic function generator that does this for you so that you don't have to put this in by hand. This is mostly just for test purposes that I'm doing it by hand here. And you can look at what some of those look like. Here I've got my frame 1, frame 2, and as expected, it's just a very simple frame 1 minus frame 2 difference. It's just an image in that two-dimensional space that's doing the subtraction. Let's keep on going to the rest of the pipeline now. Next step is imprint subtraction and failed open flagging for NIRSpec. This is not relevant to the MOS, as this is a data quality issue for NIRSpec only, so I won't go into it. The next step is flat field correction. And this is where a number of modes on the telescope are correcting for individual responsivity issues on the detector. So different pixel responsivities, different pixel effective footprints on the sky, etc. Is essentially a part of the photometric calibration that many instruments have split up into a flat field step and a photometry step. For the MOS in particular at the moment, then all of that calibration is in the photometry step and not in the flat field step. This still runs, but at the moment it's just dividing by ones, so it does nothing to the data right now. That might be something that changes by flight as we look into splitting out the sort of radiometric and the pixel-based component of our calibration. But for right now, that's actually not doing anything to the data. And so I won't show it since we just divided by 1, there's nothing to show. The next step is this source type identification. Again, I'll shift enter through those cells and then go back and talk about them. What this does is this looks in the headers of the data for information coming down from APT and the telescope to try and figure out if this is a point source or an extended source to give guidance to later steps in the pipeline. Again, since we're working with simulated data, there is no APT upstream, there is no telescope upstream, so it's looking for a lot of keywords that simply don't exist in simulated data. As such, it doesn't always get the right answer for what you intended when you're making simulations. In our particular case, I told you I'd simulated a point source, but if you run this step, you open up those files, and then you look at it, and you say, now what did it tell the pipeline the source type was? It's going to say source type equals extended. That's not right. In this case, it just defaulted to extended because it had no information from the telescope about what kind of point source it should be. So in order to get it to run correctly through the rest of the pipeline, we're actually going to kludge our files at this point to say, rather than setting all of the upstream keywords, we're just going to say, no, really, this is a point source. Let's just write that into the data and then work with that later on. So this is the kludge we've got in place, and now we can read back in the data files, and now it'll tell us, okay, it's a point source. Let's treat it as that going forward. The next step is the stray light subtraction. This is a MOS-specific step where we see when we look at short wavelengths on the detector, especially in channel 1, that there appears to be a stray light type signal that we see around the point source test data we've got in the ground campaign. It's unclear if that's really stray light or if it's actually something to do with fall-off in the responsivity of the detector, giving rise to an additional set of reflections in the detector substrate. But for now, at least, we're treating as if it's stray light, and we can readdress that during commissioning. And how we want to try and subtract that is use the narrow gaps between the individual IFU slices on the detector to measure how much that stray light signal is, model it as some low-order polynomial across the field, and then subtract that off so that it doesn't confuse the science analysis. So we can, in this case, we're calling the step. We're again looking for the output files that are produced by that step, and we can show what the science extensions look like. Here's the science data before and after stray light. You're not going to see a difference between those by eye because it's much too small of a difference to see. This is a few % type effect at best, and there is actually no stray light in MIRI sim at all. So in an ideal world, it would just say 0 everywhere for the stray light. That's not quite what it says. If you do a horizontal cut through this, then you can look and see what it's measuring for the stray light. The orange is the corrected signal, the blue is the original signal. They're very close to one another. This is a log plot. If you plot the stray light signal itself, notice this thing measured in green here. It's bouncing around a little bit more than we'd like, but that's largely because it's just seizing on noise peaks at the moment, since there is no stray light for it to measure. This is something that we're going to be fine-tuning quite a lot in calibration and commissioning, as we find out what the stray light signal really looks like when we get on orbit. If we come down next to the fringe flat, this is another MIRI-only step. This is an important step to try and correct for the fact that we see few tens of % level fringing in our data. There's a couple different points where we try and correct for this in the pipeline. This is the first and simplest of those stages, where we just say, more or less, the fringe pattern is relatively well understood throughout the entire field, regardless of what scene you're looking at. So we're going to just divide by a reference fringe flat that we determine in commissioning, and that will improve most data from the few tens of % fringing level down to the of order 10%, 5 to 10% or so fringing level. So all that it's doing here is dividing by that reference file. And if you show the before and after, you can see in this case you've got that modulation of bright and dark as you scan in the spectral dimension. That's the fringing. After the fringe flat, there is no such modulation. Of course, this is simulated data. We know exactly what the fringing is. We multiplied a fringing model in, and we've just divided it straight back out again in the pipeline. So I would expect that we could do a perfect job. With real data, then it won't look perfect after this. There'll be some residuals based on what the actual structure of the sources in your scene looked like. So there'll actually be a secondary residual fringe correction step that happens later in the pipeline that I won't be talking about today. It's still in the middle of being coded, but it's something that should be in there for cycle 1 observations, and that we'll be calibrating quite a lot during commissioning as soon as we get the telescope on orbit. I'm happy to talk about that a little bit if people are interested later. The next step is path loss correction. This is another NIRSpec only step that I won't be going into here. After that comes flux calibration. This is where MIRI is doing really all of our flux calibration and flat field correction, everything that you need in order to take the data from uncalibrated slopes into radiometrically calibrated units in units of megajanskis per steradian, so surface brightness or specific intensity, if you will. That's just using a series of reference flat fields, essentially, with photometric information in that we derive in commissioning based on looking at photometric standard stars and extended source targets as well. You can compare the images before and after. There's not much difference to see other than the stretch, but the main difference is now this one on the right is in radiometric units as opposed to arbitrary count rate units. Now we get into the arguably more interesting parts of the pipeline, where you start actually dealing with this as IFU data as opposed to simple two-dimensional detector planes. We get into this quick look cube building. So we can build a cube from individual exposures so that we can see just a quick idea of what am I looking at in each individual exposure. And these aren't necessarily things that you want to use for science because they're not going to be dithered, they're not going to have any outlier rejection. But now this is our first chance to actually see what's in the data if you can't just look at this image and tell. So if I shift enter through that, this step takes a while. So here it's just going to copy things out of the cache. But some of the files are big enough that it still takes a few seconds or so. Then this is going to ordinarily call the cube building type. The default for Spec 2 is this so-called multi-exposure type because it's combining the data from channel 1 and channel 2. You remember different channels share the same detector. They're built into a cube together, so the cubes will look a little weird with a large blank space in the middle. That's because they're really designed as just these quick look type cubes rather than full science quality cubes. If you display the cubes from two different dither positions, you get something that looks like this, where now you can actually see we're looking at it in the spatial domain. Here is a point source in dither 1, here is the point source location in dither 2. Now you get a real idea for what's in your scene. You can see, hey, it's a point source and it's dithered around the field. Similarly, there's the quick look spectral extraction that comes right after that says for each one of those cubes, run a spectral extraction on it so you can see what the spectrum looks like. This is a fairly fast step, so this is another one we're actually running in real time. You can see it now running through, pulling the extract 1D reference files that defines the aperture to use. There's an aperture correction file it pulls in as well, which describes roughly what you're expecting for aperture losses from the aperture you're putting around the object. Because MIRI has a very large wavelength range, going from 5 all the way out to 28 microns, we've actually got a circular aperture photometry that we're doing that grows gradually in wavelength as you go out to longer and longer wavelengths. And similarly, an annulus around that, where we do another kind of background subtraction. If we give that just a moment or so, then it should finish running the spectral extraction. And then it should pop out a plot for us to look at to see now what the actual spectrum of our source looks like. So here's that plot now. It's showing you something that looks a little bit odd. It's got some science data here and some science data over here and this great big long gap in the middle. The reason why is because this is a quick look spectrum of a cube built from 2 discontinuous wavelength intervals based on what's on your detector. So you have, for instance, the 1B and actually it's 1C and 2C wavelength intervals here. And then it's got a great big long gap in the middle corresponding to the 2A and 2B wavelength intervals. So that's just something to keep an eye out for when you're working with these quick look one-dimensional spectra. That's the end of Spec 2, though, and now we actually get into the, in my view, more exciting things to do with how you actually combine lots of dithered observations, how do you use multiple dithered observations to improve your data quality, etc. So Spec 3 is where you really need to start with these things called association files that folks mentioned earlier. This is how you tell the pipeline what combination of data you want to put together into your final data products. You list all of the different dithered exposures, you list background exposures, etc., everything you want to combine. There will be association files that are provided with the data you download from MAST, but since I'm going to be making a few custom files, I've also included in here some useful functions for creating association files from some arbitrary list of input files that you want to work with. And that's what we're actually going to be running the pipeline on moving forward, rather than just an exposure by exposure basis. The next step is this moving target WCS, with the idea that if you're looking at a solar system target that's moving over time, it doesn't do you any good to have a fixed world coordinate system on the background stars. You would build a cube, and the background stars stay nicely fixed, and your object flies across the field of view. That's not what you're really interested in. In this case, you want to tweak the WCS for your individual input files so that it stays centered on your object, and by comparison, the background stars drift by. That isn't relevant for this particular simulation that I'm running here, so I'm not going to bother running that step. Next one's master background subtraction. This is the second real place where we can do background subtraction in the pipeline. This is the smarter way of doing background subtraction. How this works is instead of doing a pixel by pixel subtraction from one exposure minus another, we use an exposure to determine a model of what the background is doing and extract some spectrum of that. It relies on the assumption that whatever the background is, it should be relatively constant across the MIRI field of view. At least we hope it is. We'll find out in commissioning just how accurate some of these assumptions are. Once you've got a spectrum for the background, you can then take that spectrum and broadcast it to the entire three-dimensional array. What that means is you can get much better signal-to-noise ratio for your background from a shorter exposure, rather than having to integrate for a very long time on the background instead. This is something that we're mostly tuning at the moment for use with dedicated backgrounds relevant to extended source observations. It's less well tuned at the moment for looking at point source observations, which are doing their background subtraction in the aperture photometry step instead. So for purposes of today, I'm going to skip that step as well, in the sense that it doesn't really make sense to run that on point sources just right now. This is, again, something we'll be revisiting a lot during commissioning as we learn more about what the actual mid-infrared background on the IFU is doing. Residual background matching is this next step. And the idea here is, especially for folks who are familiar with Spitzer data, the background can change sometimes relatively rapidly as you're looking at one exposure to the next, especially if you're doing a large mosaic of many different MIRI pointings. And this tries to take into account those possible changes in the background. In order to test it, we actually have to hack our data. The MIRI simulator doesn't change the background, it's fixed. So we're going to splice in a hand hack to increase the background in one of those files. Then we'll run the pipeline with and without background matching to see what it looks like. So if I scroll down to the plot, this is now the plot of the object with no background matching, where you can see now this one particular pointing is a lot higher than the other, and it leaves this strange patchwork look in your data cube. But with background matching, it identifies that one was abnormally high and brings it in line with the others. So that's potentially going to be an important part of the pipeline. The next is outlier detection, where the idea is that you should be able to use multiple observations of the same scene to look for anything that changes in unexpected ways, and now reject that as a possible outlier. Taking the same approach as before, we'll deliberately hack a column to be bad, and then see if the pipeline can pick up on that. We'll create an association file with that, and we'll run the pipeline on it with and without the outlier detection step being run. And once it runs, then we'll make a plot of what the actual data look like and what the data quality array looks like. It's going to take a moment because it needs to copy over a few different things from the cache. But as soon as that pops up, then we'll look at what the science and error extensions are. Here's the science extension. You can see this column here in white with the red cross on it that I've hacked to be bad. The data quality array has picked up on that and now flagged it in that array as well. There's a lot of other stuff in here too, due to cosmic rays and various things that were flagged earlier in the pipeline, but that's not immediately relevant. There's a couple examples in here for how you could print out the value of data quality arrays, how you could get it to tell you what they actually translate to in real terms. But that's something that you're welcome to look into later. If you look at it in cube space, here's the difference in RA and DEC between a source with no outlier detection, where you've got this glitch here, and with the outlier detection run, where it's picked up on that glitch and omitted it from the data. So I'm running short on time, but there's only a couple steps left now. The second to last one is cube creation, and we've actually been doing this a number of times already. Ordinarily, this would be one of the last steps in Spec 3, but we've been running it throughout this notebook in order to visualize what's being done with the other steps in Spec 3. Here's just an example of how you would run cube creation itself without those other steps. We take an association file, we run it through cube building, and it would produce an output data file. It takes a while, so for now it's just copying it from cache. There's a lot of different ways you can call cube building, depending on what you want for your individual science. Here's an example of how you can do it in a different way. I'm going to choose a different coordinate system for the output, for instance. And I can display the two to see what they look like. They're both point sources, but they're rotated with respect to one another. The default is the skyline method, which always has north up and east left in the cubes. There's also a IFU align method where it just aligns the cubes to be, fixed with the axes of the integral field unit slicers themselves. They're identical scientifically. They've got the same kind of content. They both have fully accurate world coordinate systems, but some might be more or less relevant for various different science cases. And finally, the last step is spectral extraction, where you take your dithered cube that's now has outlier rejection run on it. It's combined all your various different dithered exposures, and you extract a one-dimensional spectrum from it to see what it looks like. This is now going to be applying a degree of background subtraction in an annular ring around the location of the point source that you're looking at, and this gives you the science quality spectrum that you should hopefully be working with on the other end. In this particular case, it's just for a single band that I've created, so it's only 10 through 12 microns or so. But you can see now here's the spectrum of the object coming out. For point sources, then it's doing this by circular aperture photometry around the location of the object of interest. For extended sources, it has no idea where your object is. It could be an arbitrarily complicated scene. So it just sums up all of the flux in the IFU field of view to give you some idea of what you're looking at in your scene.